Yo, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And as the title of the video suggests, today's sorting algorithm is QuickSort sorting algorithm. Now before even we start off, a quick note: if you want to understand this QuickSort sorting algorithm in a very easy way, please make sure you watch this video till the end in one go, that is without taking breaks. Make sure you're isolated, make sure you do not get distracted, keep your cell phones on silent, and try to focus on this video till the end, and I can assure you that QuickSort sorting algorithm will be very easy. So yes, we're going to divide this QuickSort sorting algorithm in two parts. This first part is going to speak about its theory and the working. So in the working we will discuss the algorithm, we will go behind the scenes and dry run the algorithm just like we did in merge sort and other sorting algorithms. By the way, I have this complete data structures and algorithms playlist. If you are new on this channel, I'll drop the link of the playlist in the video description. Do check it out. There are some very important topics on data structures and algorithms. And yeah, the second part of QuickSort is going to have the implementation wherein we are going to use C++ programming to convert this algorithm into working code. Okay, so part 1 is very important if you want to understand the entire working. So again, make sure you watch this video till the end. And with that being said, let's get started. If you're new to my channel, my name is Tanmay Sakpal and I do a lot of computer science and information technology video tutorials like computer programming, development, technology talks, and a lot more on this channel. So if that's something you're interested into, then definitely subscribe and turn on the notifications to get the latest updates and never miss out on such important topics. Okay, so QuickSort sorting algorithm is a divide and conquer algorithm. Now if you've watched previous tutorials, we've talked about binary search, we've talked about merge sort, and both these other algorithms also use this divide and conquer strategy. Now this divide and conquer is nothing but a methodology, a strategy which is used by certain algorithms which breaks a larger problem into smaller sub-problems, and then you solve those sub-problems into sub-solutions and combine the sub-solutions to get the final output. Now if you're wondering why do we do this, that is because when you divide a larger problem into smaller chunks, into smaller sub-problems, it is easier to solve those. Okay? And that's where the efficiency increases. And if you've seen in merge sort, the time and space complexity was highly efficient compared to other basic sorting algorithms like selection or insertion or bubble sort. Okay, we've discussed all this and we've talked about time and space complexity also in two separate tutorials in this course itself. So make sure you watch those are absolutely important. So moving forward, QuickSort is also recursive in nature, which means that it keeps on calling itself till a particular condition is met. So it will keep on dividing the larger array or larger list into smaller chunks till a certain condition is met. In this case, it would be when the entire array is divided into one element array. So if it is 5 elements array, it will keep on dividing the array till we have only one element left. Okay, so that's the condition, and that's what recursion is all about. It keeps on calling itself. I have also talked about recursion in other video. So this thing is similar to merge sort, but the different thing or different factor in QuickSort is it uses the concept of selecting a pivot, that is selecting an element and calling it pivot. It is kind of like a midpoint. You bring that pivot to the center of the array in such a way that all the elements that are smaller than that pivot will come to the left and all the elements that are larger than the pivot will go to the right. Okay, and then you apply QuickSort on the left portion and the right portion. So this is the strategy. We'll talk about the working as we move ahead, and this is what point 2 talks about. So it picks an element as a pivot and partitions the given array around the picked pivot. Okay, we'll talk about this point and we'll take a visual explanation also. Now talking about the different versions, there are different versions in which QuickSort can be implemented, and the versions basically decide how you pick the pivot. Okay, so how you pick one particular element as the pivot defines the different versions. For example, you can always pick the first element as the pivot. So if you pick the first element as the pivot every time for this array for the first time, this will be the pivot. Another way is always pick last element as the pivot, and this is what we are going to do. So in this case, last element is this, so we pick this as the pivot. And then the third mode is pick a random element as pivot, in which case you can randomly pick any of the element as the pivot. Okay, so these are different ways or different modes in which QuickSort can be implemented. We are going to implement the second way, which is always pick the last element as the pivot. Okay, now another differentiating factor between QuickSort and merge sort is QuickSort is considered as an in-place sorting algorithm. So just like selection sort, just like insertion sort, just like bubble sort, a in-place sorting algorithm sorts the existing array in its place itself, which means that it uses swapping or substituting or replacing of elements in the same array. It does not require a separate array or temporary memory to perform the sorting. So this is what in-place sorting algorithms do. They sort the array or sort the list or data structure in that place itself, and you do not require extra memory to sort it. So this reduces the space complexity and removes the use of auxiliary array that is used in merge sort. So if you remember, in merge sort, in the merge function, every time we were merging back the sorted subarray, we were using a temporary array, right? So that is called auxiliary space or auxiliary memory, which is just nothing but extra space. We've talked about space complexity, and in this merge sort, since at every merge step we have to create this temporary array, some extra memory is utilized, right? So that is not required in QuickSort, and hence QuickSort is considered to be more space efficient compared to merge sort. So hence QuickSort is also one of the most efficient sorting algorithms, and if you observe, the time complexity is n log n, which is pretty much similar to merge sort. However, the space complexity is O of log n. In merge sort, the space complexity was n, and log n is kind of less than n on the graph if you plot it, and hence QuickSort is a little bit more efficient when it comes to space complexity. So this was a little bit of theory, and this is the array that we are going to use in our example. It is going to be an array of size 5 and having elements 7, 9, 3, 2, 6. And talking about this point, that is, the second point, it picks an element as a pivot and partitions the given array around the picked pivot. So just to give you a visual representation, let's say we have this array, and this is our array, right? 7, 9, 3, 2, 6. Now we are going to use this mode, that is always select the last element as pivot. So in step number 1, that is in first QuickSort, we are going to select this as pivot. And what we will do is, after this one step of QuickSort, this 6 will be positioned in this array in such a way that all the elements that are larger than 6 will come to the right hand side of the 6, and all the elements that are smaller than 6 will come to the left side. So let's see which is larger. So if 7 is larger than 6, 7 will be placed over here. 9 is larger than 6, 9 will be placed over here. 6 will come in the center. 3 is smaller than 6, 3 will come over here. 2 is smaller than 6, 2 will come over here. And this is after step number 1. Okay, so we have multiple recursive steps, and right now the array is not sorted. Obviously it is not sorted in one step, but if you observe, what has happened is 6 has come in the right position, in the center position where it should be. So now this pivot that was 6 value has come in the center position after one step. Now if you observe, 2 and 3 on the left hand side are kind of sorted, and 7 and 9 is also sorted, but this may not be the case. It can also be 3, 2, 9, 7, something like this. I was just showing it for representation purpose, but after step 1, what will happen is the selected value, the pivot, will come in such a position where on the left hand side of the pivot will be all the elements that are smaller than that pivot value, and on the right hand side of the pivot, all the values will be greater than the pivot value. So this is still not sorted, but now what we will do is we will apply QuickSort again on this subarray and this subarray, because 6 has come in the right position, right? So now we have to apply QuickSort over here for these two elements and these two elements. So 2 more QuickSort calls, and so on. It will progress till the entire array is sorted. Okay, so I hope you're getting a little bit of the working. Of course, we still have to see the algorithm, and we will dry run this algorithm also. But I just wanted to give you an overview about how this pivot is selected and brought to a position where all the elements to the left are smaller than that value, and all the elements to the right are larger than that pivot value. So this is the entire concept at an overview level. Now what we'll do is, let's take a look at the steps that are involved in the QuickSort sorting algorithm. So at an overview level, in a step-by-step representation, or you can say this is kind of like a English version of the algorithm, we have the function name QuickSort, we have the array ARR that is passed, S and E represents the start index and end index. So there are 3 major steps and 2 parts basically. If you've seen the merge sort, there was a 4th or 3rd part which was merging, but over here we don't need to merge it. So step number 1 is find the partition index. So we need to find where exactly are we supposed to partition every time, right? So that partition index is supposed to be found out, and this is where the recursion will happen, because this partition will keep on happening till the start index is less than end index. Obviously, start index will be less than end index for every time till we have only one element in the subarray, right? When we have only one element in the subarray, either the start index and end index will be equal, or the end index will go below start index. So you'll see that in the working, don't worry. But this is where recursion will happen, and we will keep on calculating the index where we are supposed to partition or find the pivot value. Okay. Now this partition is a separate function which is called inside QuickSort. So QuickSort is a function, or you can say is a method. Inside that we are creating another partition function which will take that same array and same start index and end index. And here is where the division is gonna happen. Division is where we are finding the pivot point or partition point to be divided into two subarrays. Now moving on to step 2 is where we call QuickSort for the first half, and step 3 is called QuickSort for the second half. Now we just found out P, which is the partition point. Then we will say QuickSort of array. We will say start index as S only, but now the end index we will pass as P minus 1 because we just found out the pivot point, right? So again, taking the example of 5 element array with the same example 7, 9, 3, 2, 6. So after first time we were having 6 in the middle, we were having 3, 2, 9, 7, something like this. This is just for representation. And now when we are calculating P, we will get something like this point, right? So when we say QuickSort of ARR of S, S is gonna be 0, and this is 0, 1, 2, 3 and 4, and this time P we will get as 2. So 2 minus 1 will equal to 1. So we will run QuickSort, that is this QuickSort for 0 to 1, and the step number 3 is saying QuickSort for the second half, which is this half. So it would be P plus 1, that is 2 plus 1, that is 3, to end index, which is 4. Okay. So we will again call QuickSort recursively. So QuickSort is this function, and we are calling QuickSort again. So this is a recursive call, and over here is also a recursive call, kind of like what we were doing in merge sort, but this time it is on the two separate subarrays. And the sorting part is happening in the partition function itself. So if you are wondering where exactly is the sorting also happening, it is happening inside this partition function. So the entire crux of this entire code is inside the partition function and not in the QuickSort function. Okay. So QuickSort function is just used to give recursive calls to do the partitioning and to do the in-place sorting. So this was just an overview way. If you want to note these steps down, if you want to prepare your exam answers, you can completely note these steps down. And now what we'll do is we'll move to the actual algorithm. Okay. Okay, so on the right hand side, as you can see, I've converted these 3 steps into a function way, into an algorithmic way. This is still not proper syntax. Okay, so this is not C++ syntax. Even though it does look like it, it is still not proper code. So this is sort of like a pseudocode representation. So the same step number 1, you can see we are calling the QuickSort over here. We are passing the array and start index and end index. Step number 1, find the partition index till start index is less than end index. So that condition is called over here in the if block. We are saying if S is less than E. First step is to get the partition index. Second step is to call QuickSort for the first half, that is S and P minus 1. And the third step is another recursive call for the second half. Okay, or the second partition, which is P plus 1 comma E. Simple enough. This is the QuickSort function representation, but the real game or real working is actually happening in the partition function. So now let's see how the partition function progresses. Okay, because this is very important. Okay, so as you can see on the left hand side, I have shown you the partition function or partition algorithm. These are the steps, different steps that are gonna happen in the algorithm. And on the right hand side, I have drawn a basic diagram of how the algorithm is gonna progress. So the best way to understand this QuickSort sorting is to dry run this entire algorithm. Okay, so we will go step by step, right? So we'll understand what is happening at every step in the partition function also. And the best way, as I mentioned, is to implement these two functions onto this array. So this is our array, and now we are applying QuickSort on this. Okay, so let's start with step number 1. So step number 1, obviously first call QuickSort. So let's see how that call would look like. Okay, so the first QuickSort call has happened. Okay, because it is a recursive function, we will have multiple QuickSort calls. So I've denoted it by number 1, and QS stands for QuickSort. We are passing the array ARR. Okay, I have not used brackets, but understand that this is just representation. And the start index obviously for the first time is going to be 0, end index is going to be 4, right? So when we call the QuickSort function, for the first step is if S is less than E. Now what is S over here? 0, right? We are passing 0 over here. What is E? 4. Is 0 less than 4? Yes. So this condition is true. We will go inside the if block. First step itself is get the partition index P, and for here we are calling another function named partition. We are passing the same array with the same S and E. Okay, because S is 0, E is 4. Now from here we will jump to this partition function. So this is where the real game is happening, real crux is happening, right? So now let's try to go step by step with the partition function. We are passing the same array ARR. We are passing start index as 0. We are passing end index as 4. Now, according to our mode of implementing QuickSort, remember we were saying the pivot that we are going to select is always going to be the end value of the array or subarray. In this case, ARR of E is ARR of 4 because E is 4, right? We've passed E as 4. So ARR of 4 is going to be what? 6. So for the first time, this is going to be our pivot value. Okay. So pivot I'm going to write over here is 6. So every time we are going step by step in a dry run scenario, always note all the variable values so that you understand what is happening at every step. So what you can do is you can take a pen and paper yourself and dry run along with me. Don't take a pen, take a pencil because you'll have to probably erase a lot of things. But that's the best way to understand such algorithms, by dry running them on pen and paper or whatever you have. And then you'll understand it in a much better way. Okay, so moving ahead, the next thing is we create another variable and we say P index is equal to S. So S over here is 0, right? So P index obviously initially is going to be 0. So this P index, I'll tell you why we're using it. But in the overview, what I've told you is when we select one pivot, what we want to do is all the elements that are smaller than the pivot have to come to the left hand side of the pivot value, and all the elements that are larger than the pivot value have to come to the right hand side. So that is something that we have to do in this function itself. That's what I've told you. So we have to do the comparison in this partition function only. So this is where the comparison will now start, right? Because we want to compare every element with this pivot value and see if it is smaller or larger, and depending upon that we have to position it accordingly. So in the for loop, that is the third step, what I'm doing, I've set P index of S, which is currently 0. It will vary from different subarrays. Right now it is 0. So I'm saying for I is equal to S. So for I is equal to 0 to E. So what is E? E is obviously 4 this time. So this for loop will run from 0 to 4. Now inside this is where the comparison is happening. So now I'm saying if ARR of I is less than or equal to the pivot value. If it is less than or equal to the pivot value, what we are doing is we are saying swap ARR of I and ARR of P index. So let's understand this with step-by-step explanation and I'll tell you what is happening. So for the first time, ARR of I is ARR of 0. What is ARR of 0? ARR of 0 is 7. So we're saying if 7 is less than equal to, what is pivot value? Pivot value we've decided as 6. Is 7 less than equal to 6? No. So this entire if block will not be executed for the first time, right? So it's not executed. Now we will come at the end of the if block, we will come outside the if block. Again for loop now will become plus plus because it is a for loop, it is running from 0 to 4. So let me just erase all these values. So it's running from 0 to 4, right? And now I has become 1. Now we will again go inside for loop. We will say if ARR of 1, what is ARR of 1? ARR of 1 is 9. Is 9 less than equal to the pivot value which is 6? No. So again this entire if block will not be executed. Alright, so let me erase this. Now I will become 2. We will say if ARR of 2, that is 3, is 3 less than or equal to the pivot value which is 6? Yes. Now the condition has become 2. So this 3 is less than 6. So according to our strategy, what is our strategy? We want all the elements that are smaller than 6, that is smaller than the pivot value, to come to the left hand side of the 6 value. So what we are doing now is we are going to switch, or we are going to take this 3 value and put it at the very start of the array because we want smaller elements to the left hand side, right? So this is what is happening over here. Okay. So when we go inside the if block, we are saying swap ARR of I. What is I now? Right now I is 2. So ARR of 2 is 3. So swap 3 and ARR of P index. remember we set P index as 0, right? So let me write it over here also. Initially P index was 0. So ARR of 0 is this first position in the array, which is 7. So we have to swap 3 and 7. So 3 will come over here and 7 will go over here. And the reason why we are doing is, as I mentioned, 3 is smaller than 6. So obviously 3 has to come to the left hand side of the pivot value. So we are already keeping 3 at the very leftmost value. So after this entire algorithm will execute, 3 and 2 will come to the entire left side and 7 and 9 will shift to the right side. This is the strategy. Okay. So after swapping, let's actually write it over here. 3 is shifted over here. 7 is shifted over here. Okay, let's keep 9 and 2 and 6 as it is right now because the algorithm is still not executed. Now P index will become plus plus, so P index will now become 1. Right? This is what is happening over here. P index has become plus plus. Again, we will come at the end of the if and we will go to the start of the for loop. What was I? I was 2. So I now will become 3. Okay, let me just erase it off. So I will become 3. Also, one more thing to note that is the for loop will run from I equals to S to E minus 1. Okay, and not E because the last element obviously is the pivot. So we only want to compare 7, 9, 3 and 2 and not the last pivot value with itself, right? So this will run from 0 to 3 only. So I've made a little mistake over here. It is E minus 1. I hope you guys rectify it. So now I will become 3. Okay. And now we are again going to check if ARR of I, which is ARR of 3. What is ARR of 3 over here? It is 2. And you can now use this newly created array because we have just swapped 3 and 7. So now all the comparison should happen over here. So this is 0, 1, 2, 3 and 4th index position. So we are checking ARR of I, which is 3. So at 3rd index position we have value 2. So is 2 less than equal to the pivot value? What is pivot value? 6. Yes. So we will again go inside if. Now we are saying swap ARR of I, that is 2, because ARR of 3 is 2. We have to swap this with ARR of P index. We just incremented P index by 1 value and now P index has become 1. What is the value at 1 position? Right now it is 9. So now we are swapping 2 and 9, right? So 2 will come over here, 9 will come over here. Let's do the swapping. Okay, so the swapping is done. 2 has come over here, 9 has come over here. Again, P index will be incremented. So now P index will become 2, right? This is P index plus plus. So we'll come outside if. We will come at the end of the for. For will get incremented and I now will become 4. So obviously the for loop will not execute because this for loop is going to run from 0 to 3 and not 4. The last value obviously is the pivot value. We don't have to do the comparison for this pivot value. We have to compare all the remaining elements with the pivot value, right? So that's how the comparison will happen. Now we will exit outside the for loop to the last swapping. So if you've understood this so far step by step, we have arrived at this array 3, 2, 7, 9, 6. Our pivot value 6 is still at the end of the array. So what we did in this partition function so far is all the elements that are smaller than the pivot value 6 we have brought to the left hand side. You can see 3 and 2 are to the extreme left. Now the only thing remaining is to take this 6 and put it at the position of 7 such that once you do this, 6 will come over here and then we will satisfy the condition where we were saying that we want all the elements smaller than the pivot value should be on the left hand side, because when 6 will come over here, 3 and 2 are smaller than 6 and 7 will go over here. So 9 and 7 are larger than 6. So that is the strategy, right? So this last swap is saying swap ARR of E. What is ARR of E? E is the last element, which is 4, which is the pivot value. So swap 6, comma, ARR of P index. Now remember P index has come to the point of 2. So we are having index position 2 over here, that is 7. So 6 and 7 is now swapped. So that's the reason why we want P index to keep a track of the positions in the array. Okay, that's the purpose of P index. So now we will swap 6 and 7. So 6 will come over here, 7 will come over here, and this is the last swapping that is happening, and ultimately we will return P index. What is P index over here? It is 2. So this is returning P index, and remember we had called partition function over here in the QuickSort function. and partition function is on the right hand side, which means that it is going to return an integer value and it will be stored in this partition p variable. So p variable is waiting for an integer value which is going to be the index position where the partition is going to happen, and that is this p index. So p index is 2 and it will be returned from this partition function and it will be stored in this p variable. Okay, so this is one entire iteration of partition function and this will result in p value of 2. So this p over here in yellow I have marked, this value will become 2. Okay, so after the one full iteration of the partition function, we are getting this array 3, 2, 6, 9, 7. So the only thing that has happened over here is the value that we selected as pivot has come to the proper position in such a way that all the values to the left hand side are smaller than the pivot, all the values to the right hand side are larger than the pivot. Now if you observe, obviously this array is not sorted. 3, 2, 6, 9, 7 is not sorted in ascending order or descending order. In fact, it is not sorted at all. We want to sort it in ascending order. So it should be 2, 3, 6, 7, 9, right? So right now it is not sorted. Obviously we are only at step number 1. We just gave one QuickSort call. So in that first QuickSort call, we just called the first line, first partition function, and it has returned a value of 2. Now the first QuickSort call will continue to the second step. But second step over here itself is a recursive QuickSort call. So let me just first erase out some content from this, otherwise it is gonna get very cluttered. Okay, so we are at step number 2 of the first QuickSort call, and step number 2 of the first QuickSort call is a recursive call to itself, right? So in this case, what will happen is this first QuickSort will now be paused. Okay, so the first QuickSort function is calling another QuickSort. Obviously it will go in the pause state. So that is how recursion progresses. I hope you know this. So first QuickSort call is calling second QuickSort and it is pausing. In the second QuickSort call, we are passing the same array. We are passing the start index as s only. S is, remember, it was 0. So let me just write it over here, 0. End index was 4, right? So you can see it over here also, 0 and 4. But for the end index, we are saying p minus 1. Now we just got the p value as 2 from this one partition function call. So 2 minus 1 is going to be 1. So for this QuickSort, that is the second QuickSort call, we are passing the same array, but start index s is going to be 0 and end index is going to be p minus 1, that is 1. Okay, so end index is equal to 1. So this is how the second QuickSort call will look like. So first QuickSort call is paused and we are giving a call to the second QuickSort. QS represents second QuickSort. Start index, as I mentioned, is 0. End index is p minus 1. P we just got as 2. So 2 minus 1 is 1. Okay. So we are passing ARR 0 and 1. So a second QuickSort is called now. Let's start from the scratch. So I'm going to erase this. Okay. So first QuickSort, as I mentioned, has called second QuickSort. We have passed 0, 1. And now this is going to be 0 and comma 1. So again, starting from the very first step of QuickSort function, it's a recursive call. We are saying if s is less than e, s is 0, e is 1. Obviously 0 is less than 1, so it is true. So we will go inside the if block and again we are calculating a new partition value by saying p is equal to partition of ARR s and e. Now this time s is 0 but e value is 1. Okay, so partition is giving a call to this function. In this we are passing s as 0, e as 1. So that's the only difference. So 0 and 1. Now I have to calculate pivot, p index and p inside this partition function. So again the same thing, repeat story is happening. So pivot over here is ARR of e. This time e value is 1. Okay. And now we have to use this array as the fresh array. We cannot use the previous array. We've already made changes to the same array. Remember, this is an in-place sorting algorithm. So every step is happening on the same array and not any temporary array. So now we have the fresh array of 3, 2, 6, 9, 7. What is ARR of e? It is ARR of 1 because e this time is 1. You can see I've written e as 1. ARR of 1 for the fresh array is 0, 1, 2, 3, 4. 1 is 2, right? So this is going to be 2. So pivot this time is 2. So essentially what we're doing is we are applying QuickSort because we are at this step of the first QuickSort. We are applying QuickSort on the left partition. So we got 6 in the middle after the first step. So the two parts that we have is this is one part and this is second part. So we are applying another QuickSort call which is going to happen to the left hand side. So for the left hand side, that is left sub array or left sub partition, which is the last element, obviously 2. Hence we are selecting the ARR of E, that is ARR of n index, that is value 2, which is stored inside the pivot. Okay. So pivot is done, pivot value is 2. Next is P index is equal to S. S is obviously 0. So P index initially is going to be 0. Now we are again going to say for I is equal to S to E minus 1. So this is E minus 1. Let me actually make this change over here itself right now. Okay, so I is equal to S to E minus 1. Right? So what is S? S is 0. E minus 1. E is 1. E is 1. 1 minus 1 is 0. So from 0 to 0, it means that this for loop will run only one time. Because we only have two elements in the left sub array, that is left partition in this case. So in this case we are saying if ARR of I, what is I? I is 0 initially. So ARR of 0 is 3, right? ARR of 0 over here is 3. So is 3 less than or equal to the pivot value? What is the pivot value over here for the second iteration or second QuickSort call? It is 2. Is 3 less than or equal to 2? No. So this entire if block will not be executed. We will come at the end of the if. We will go at the for will become plus plus. I will become 1. And we are only running from 0 to 0. So this for loop also will stop running. So now we will come outside the for loop. So coming outside the for loop is the last step of the last swapping. And the last swapping says ARR of E. What is E? 1. What is at index position 1? 2. So swap 2 with ARR of P index. What is P index? P index we set as P index is equal to S, which was 0 only. So P index never got incremented because we did not go inside the if block. So what is the value at 0th index? It is 3. So you have to swap 2 with 3. So 2 will come over here, 3 will come over here. So that is what is going to happen over here. So I'm going to write it 2 and 3. Let me write it in green. So 2 is over here, 3 is over here. Let's keep this 6 as it is. By the way, these are not separate sub arrays, okay? So I've just marked them 0, 1, 2, 3 and 4. So this is the same ARR only, but I have represented it in separate blocks. Ultimately it is the same array only, it is not divided. You can make it out with the index positions also. So 6 is always going to be in the middle. We've just sorted the left hand side. You can see 2 and 3. So 2, 3, 6 is pretty much sorted now. Okay. So we did the swap. We will say return index. That is return P index. What is P index? P index is still 0. So 0 will be returned over here. And now it will be stored in the P value of this QuickSort call. This QuickSort is the second QuickSort call. Alright. In the second QuickSort call, we are at step number 1, which is get the partition index. What is the partition index that we got? 0. So I'll write 0 over here. Now we will move to the next step in the second QuickSort call. But if you observe, the next step itself is a third QuickSort call, that is a recursive call, which is going to apply QuickSort to the left side of this subarray. What is the left side of this subarray? It is going to be a single cell element, right? So here the QuickSort will be the same array, that is this entire array, but here the S is going to be 0 obviously. But now we are going to say P minus 1. What is the P that we just got? From here we got P as 0. Remember, we just got 0. So 0 got transferred and stored in this. That is what I showed over here with this entire arrow. So 0 minus 1 is going to be minus 1. So a third QuickSort call is given with values of ARR, S as 0 and E value, that is n index, as minus 1. Now obviously we don't have minus 1 as index values. So let's see what happens. So of course third QuickSort call is called, which means the second QuickSort is going to go in the pause state. So this QuickSort will now become paused. And a third QuickSort call is given. So let's see that call. So second will be paused and a third QuickSort call is given, and this is how it looks like. Start index is going to be 0. End index, as I mentioned, is P minus 1. P we just got as 0. So 0 minus 1 is minus 1. So n index is -1. So again this entire QuickSort will be called. So let's start from the scratch. So for the third call, that is third QuickSort call, the array is passed as it is, but we are passing start index as 0, end index is -1. Obviously -1 does not exist in array indexes, and that is handled in this if condition. This if condition says, is s less than e? What is s? 0. What is e? -1. Is 0 less than -1? No. And this is where the recursion breaks, because now this if block has become false. S cannot be greater than the end index. The start index can never be greater than the end index. S is 0 and E is -1, which means start index has become greater than the end index. And this condition will never exist. It is an invalid condition. So now the entire if block will not be executed and QuickSort will stop. That is, this entire if block will not be executed. We will come at the end of the function over here, which means this QuickSort has done its execution. This is a third QuickSort call. So who called the third QuickSort? The second QuickSort, right? So now we will go back, which means from third QuickSort we will go back to the paused second QuickSort. So now this will no longer be paused. It will start its execution again. Remember, the second QuickSort had paused at step number 2. That is the third QuickSort call. So it will go to step number 3, and the step number 3 is one more QuickSort call, but this is for the right side of the partition or the rightmost partition. So over here at this step we have S as 0 and E as 1. So we will give one more QuickSort call, that is this QuickSort call, and this QuickSort is gonna say the same array, but the start index is p plus 1. So at step number 2 or at this level of QuickSort, what is p value? P value is 0. So 0 plus 1, 1. What is E value? E value is 1. We will pass as it is. Okay. So a fourth QuickSort call is called from second QuickSort call. So again this will become paused. Let's see what the fourth call is. In the fourth call, as I mentioned, the start index is 1. That is p plus 1. P is 0 over here. So 0 plus 1 becomes 1. E is also 1. So we are saying QuickSort of ARR 1, 1. So a new QuickSort is called. Let's see what this QuickSort will be. So S is 1, E is 1 in the condition if S less than E. Is 1 less than 1? No. 1 is not less than 1, right? So again, this entire if block will not be executed, which means QuickSort will not go into a recursive call. One more recursion will not happen. So this QuickSort will be done. So this second QuickSort had called fourth QuickSort, and fourth QuickSort is done its execution. So it will come back now to this. Okay. And 2 and 3 will remain as it is. So nothing happened to 2 and 3. They were as it is because the recursion broke off at third and fourth QuickSort call. They did not go inside. We did not call the partition. We did not call multiple QuickSorts. So 2 and 3 is already resolved over here also. Let me write 6 also as it is. You can see on the left hand side, the left branch is pretty much solved. So coming from fourth QuickSort back to second QuickSort, the second QuickSort had come to this step, and after this step the if block will complete itself. We will come outside this QuickSort also. So second QuickSort will also be done. So erasing this off. Who had called second QuickSort? First QuickSort, right? First QuickSort was paused and it called second QuickSort. So we will go back from second QuickSort to the first QuickSort. Now at this level, when we come back to the first QuickSort was paused at step number 2 itself, right? So it had paused over here. That is, first QuickSort gave a call to second QuickSort. So first QuickSort gave a call to second QuickSort. And this QuickSort is done now. The left hand side QuickSort is done executing. So second QuickSort came back to the first QuickSort. That is how recursion works. But now it will move to the next recursive call. But this time the QuickSort will be called on the right hand side. So it will be called on this subpartition. So at this level, at the top level of first QuickSort, we have S as 0 and E as 4. We also have got the P value of 2. So a fifth QuickSort call will be given because we've called 1, it is over here, we've called 2, it is over here, we've called 3 and 4. So 4 quicksort calls have already happened. Now a 5th quicksort call will be given, but this time it would be for the right hand side. So we are passing the array, we are saying p plus 1. So at the level 1, at the top level, p is 2. 2 plus 1 is 3. And what is e? E is 4 at the top level, right? So 3 and 4. So 3 and 4 are these two indexes. So we are only gonna call quicksort for these two values. So let's see how the 5th call looks like. Okay, so now the first quicksort is giving a call to a 5th quicksort recursively. So I hope you are getting how the entire algorithm is progressing, how the recursion is working. In the 5th quicksort, the start index is 3, the end index is 4. So now let's actually calculate, or let's start from the scratch or start of this quicksort function. So start index is 3, end index is 4. Is 3 less than 4? Yes. So we'll go inside the if block. Now again the partition function will be called. At this level we have to calculate pivot, p index and everything. So let's start with the partition. So partition function will be called. We'll come over here. S is 3, E is 4. Pivot is ARR of E. E is 4. What is ARR of 4 over here? It is 7. So now pivot value becomes 7. P index is equal to S. S is 3, right? S is 3. So value at 3 is 9. So p index becomes 9. Let me write it over here also. P index becomes 9. We are saying for I is equal to S to E minus 1. What is S? S is 3. From 3 to E is 4. 4 minus 1 is 3. So from 3 to 3, which means it will run only one time. This for loop will run only one time. We will go inside. We are going to say if ARR of I. What is ARR of I? Initially I is equal to S. S is 3. ARR of 3 is 9. Right? So this is ARR of 3. It is going to be 9. Is 9 less than equal to the pivot value? What is pivot value? We just said pivot value is 7. Is 9 less than equal to 7? No. So this entire if block will not be executed. We will come outside the if block. We will go to the start of the for. For loop, as I mentioned, is only gonna run one time. So we will come outside the for loop to the last swapping. And at this swapping we are saying ARR of E. What is E? E is 4. What is value at 4th position? 7. We have to swap 7 with ARR of P index. P index, as I mentioned, is okay. P index is supposed to be S. Okay. S is basically 3. So this is the P index and not 9. So the value at position 3, that is ARR of P index, which is ARR of 3, is 9. So we have to swap 7 and 9. Because 7 is obviously smaller. So 7 will come over here and 9 will come over here. So ultimately we will have 7 and 9. Let me write it in green because it's sorted. And lastly we will say return P index. What was P index? P index was 3. So 3 will be returned back from this partition function and it will be stored in this P variable. Now we are at QuickSort, which is a 5th recursive call. We've just calculated P as 3, right? P index was 3. It is returned and stored in the P value of the QuickSort call. Now again we will do a QuickSort. We will say ARR of S and P minus 1. S at this level is 3. So we will say 3 comma P minus 1. P we just got as 3. So 3 minus 1 is 2. Now if you observe, obviously this QuickSort will not execute because start index is 3 and end index is 2. Obviously this can never happen, right? Start index can never be greater than the end index. So a 6th QuickSort call will obviously be given. Let's see how that goes. So a 6th QuickSort call will be given. So this 5th QuickSort will become paused and a 6th QuickSort will be called. But here S will be 3 and E will be P minus 1, that is 3 minus 1, which is 2. So that's why 3 and 2. But in the if block, when we call the QuickSort again, we will compare if S is less than E. And over here S is 3. Is 3 less than E, which is 2? No. So this entire QuickSort will not be executed at 6th QuickSort call. So this will be done. So this is done and it will come back to level 5, that is 5th QuickSort call. When it will come back at 5th QuickSort call, a 7th quicksort will be called from 5th quicksort, which is for the right hand side or right partition. And over here we will say, that is this quicksort, it would be p plus 1. P is 3, right? So 3 plus 1 is 4. E obviously at level 5 or 5th quicksort is 4. So 4 comma 4 will be passed. And again in the quicksort we will check if S is less than E. So is 4 less than 4? No. So 4 and 4 will be passed. And obviously this quicksort will also be done. So 7 and 9 will remain as it is. They are already sorted basically. So these last two quicksorts and these two quicksorts were just called for the sake of calling. But the condition was never true. So multiple recursions did not happen. If you give a wrong condition over here, you will go in infinite loop, infinite recursive calls. But anyways, coming back, 7th quicksort will go back to 5th quicksort because 5th quicksort had called 7th. Remember that this 5th quicksort was called by the first quicksort and it is still paused. So 5th quicksort will get done at the last step and this will also be done and it will return back to the calling function, which is the very first quicksort. When it comes back to the first quicksort will also be done because the first quicksort is done calling quicksort for the left hand side and the right hand side. You can see it is called quicksort for the both sides and it has become very cluttered right now. I know it is looking very shabby, but ultimately if you see at the end, the result is what we've got is a sorted array. If you observe these values, 2, 3, 6, 7, 9 are in a sorted way. And this is the same array that we had, ARR only. I have just separated or added space in between, but ultimately this is going to be 2, 3, 6, 7 and 9. Okay. So this is how the entire quicksort sorting algorithm works. These are the two different functions and this is how recursion works and the partition function works. So yeah, that's it for this video guys. I hope you've understood the entire behind the scenes of the entire working. We've dry runned each and every step and we've seen how the recursion progresses, how one quicksort calls another quicksort, and in every quicksort how the partition function is working and doing the in-place sorting. And ultimately at the end we are getting the sorted array in ascending order because we've applied quicksort to sort a random array in ascending order. So that's it for this video guys. If you like this video, please give it a thumbs up. Let me know in the comments how quicksort sorting algorithm was. Did you find it easy? If you have any doubts, go back. You can watch this over and over again. If you don't know what recursion is, do watch that video. I will link it in the video description. And if you've missed any of the DSA tutorials, if you don't know time and space complexity, all those videos are there in this course. Make sure you watch all of them because those are very important. And I'll see you guys in the part 2 where we will use this same algorithm and we will write a C++ program to implement quicksort sorting in C++ programming. So thanks for watching. See you in the next one. Peace.